So in section 3.3, we're going to be introducing a new topological property, and that's what it means for a set to be compact. So far, we've studied three topological properties. We've talked about open, closed, and bounded. Technically, we've only talked about bounded in the context of sequences, but a set being bounded is defined analogously. So if I have a set A, it's bounded if there exists some capital M such that for any element I pick an A. So that's kind of like for any sequence element. The absolute value of A is less than or equal to M. And that's just a way of saying that given this closed and bounded interval negative M to M, your set A has to lie somewhere in here. So I'm going to start by giving you the definition of compact, and then we're just going to take a step back and look at it and say, what's familiar about this? So here's our definition. A set K that's a subset of R is compact. And we abbreviate this CPT, provided every sequence Xn that's a subset of K has a subsequence XnK such that XnK converges to X, where X is also an element of K. At this point, looking at the definition, you should be saying, this looks familiar. There are two things going on here that should sound like things we have done before. The first is the existence of a convergent subsequence. So remember that the Bolzano-Weierstrass theorem could be used to guarantee, so this guarantees the existence of a convergent subsequence. When a sequence is bounded. And the second one is this part where we're saying not only do we get a convergent sequence, but we also get this requirement that the limit ends up back in the set. And that sounds kind of like closed. So we know that closed sets contain the limits of their convergent sequences. So a natural question that you might ask would then be, okay, well, if this sounds so similar to being bounded and so similar to being closed, is there a relationship between bounded, closed, and compact? And we'll see later that there is. For now, we are going to go and take a look at just getting to know the definition of compact and working with it that way. And we'll go through some examples. As a first step, I want you to take the time to try to write out the definition of what it means to be not compact, because there's kind of a subtlety going on here. So in particular, we want to be able to answer the question, how would we show that a set A is not compact? So let me write that down. So how would we show that a set, well, I guess I could call it K, a set K is not compact? So I would pause the video here and try this on your own and think it through, and then come back and see what I have to say. So if I want to show that K is not compact, I need to find a sequence, Xn, that is a collection of values in K, such that either one of two things happens. To see what those two things are, let's go back up to our definition of compact. So this says a set is compact if every sequence has a subsequence that converges to a limit in K. So the negation from a high level perspective would be, well, I've got to be able to find a sequence that doesn't have a subsequence that meets this property. But there's two properties going on here. The subsequence has to converge and its limit has to be in K. So that negates to an or statement. So either it's got a sequence such that every subsequence Xnk diverges, meaning it doesn't have, meaning Xn doesn't have a convergent subsequence. That would be one way to fail the statement. Or it could be that Xnk, like if Xnk converges to X, then X is not an element of K. So what we're saying here is either every subsequence diverges and you don't have any convergent subsequences, or if you find a convergent subsequence, it converges, but its limit doesn't stay inside the set. So we have two ways that we can approach proving a set is not compact. So what I would like for us to do now is to take a look at an example. I want to determine whether the following sets are compact. So we've got A being just, we'll go with the closed interval 0 to 1. We've got B, it is the open interval 0 to 1. And then C is another interval that we've shown to be closed, but this one is not bounded. So let's write out the properties that we know about each one of these. So in the first one, we know the first one is closed. We know it's not open because of the endpoints. The endpoints won't have epsilon neighborhoods around them. And the other property we can talk about is bounded, and we do know that this is a bounded set. It's bounded by the number m equals 1. The next one is not closed. It is open, and it's still bounded by 1. And the final one is closed, not open, and unbounded. So I would take a moment to think about what's going on in each of these sets and whether or not you think that given an arbitrary sequence inside the set, can you guarantee the existence of not only a convergent subsequence, but a convergent subsequence whose limit is a member of the set? Okay, so we are going to go over these now, and I want to start, I'm actually going to tell you the answer to each of them, and we're going to go through them one by one here. So the first set, the answer is yes. The second set, the answer is no. And the third one, the answer is also no. There are some important facts that are going to be helpful for us as we try to prove that a set is not compact. Because remember what we said we had to do. If a set is non-compact, we're either going to have to argue that every subsequence diverges, or we're going to have to argue that every convergent sequence is going to have to go to an element outside the set. So every convergent subsequence. So that first one, trying to argue that every subsequence diverges, we have experience doing that. We know that when you have a monotonic divergent sequence, then we can argue that every subsequence has to diverge as well. So that's going to be an important fact. So if xn diverges and is monotonic, then every xnk also diverges. So that'll give us an idea for how we might come up with examples of sequences that could prove that a set is not compact simply by demonstrating that sequence doesn't even have a single convergent subsequence. And then the second one, this idea of trying to say, well, okay, I have a sequence, but every convergent subsequence is going to go to a value outside of the set. It'll be important for us to remember this fact, that if you start with a sequence that is convergent itself, then every subsequence is going to have to go to that same limit. So every subsequence, in this case, would go to x as well. X and k goes to x. So this is important enough that it should go in a box, because this will help you in your homework. You're going to have to identify whether or not sets are compact, and when they're not, you're going to have to produce a sequence that gives us a counterexample to the definition of compact. Okay, so let's take a look at this first problem. So the set A equals 0, 1. We've noticed here that it's closed and it's also bounded. And those two properties are really important. Because remember when we introduced the definition of compact, we said, this sounds really familiar. We know that bounded sequences have convergent subsequences using the Bolzano-Weierstrass theorem. And we know that closed sets have convergent sequences whose limits stay in the set. So we can actually prove this by applying the Bolzano-Weierstrass theorem first to get the subsequence, and then apply closed to say its limit stays inside the set. So let's take a look. So we're going to say A equals 0, 1, closed like that, is compact. And the proof. The definition of compact says we need to prove that for any sequence in my set, I can find a convergent subsequence whose limit stays in the set. So I'm going to introduce an arbitrary sequence. So I'm going to say let xn be a sequence in 0, 1. Because A is bounded, by the Bolzano-Weierstrass theorem, so by BW, there has to exist an xnk such that xnk converges to x, where x is a real number. But since xnk is a subset of A and A is closed, we really have a convergent sequence inside a closed set. X has to be, therefore, an element of A. And so what we've demonstrated is for an arbitrary sequence in the closed interval 0, 1, we're able to find a convergent subsequence whose limit is in A. That is the definition of compact. So by definition, A is compact. So now let's take a look at the set B. So B, we said here we've got the open interval 0, 1, but the important facts that we want to point out here is that this set fails to be closed. It is bounded, however. And the reason I'm talking about these two properties, again, is because we know bounded sets allow us to use the Bolzano-Weierstrass theorem, and closed sets allow us to say that convergent limits have to stay inside the set. Now, in this case, what we get is that we are not closed. And when you're not closed, the important fact we would like to use here is going to come from number 2. So I'm going to write this in our fact box. If I'm not closed, I might want to use number 2. If I'm not bounded, I might want to use number 1. So we're going to say instead, we're going to use the fact that we're not closed to demonstrate the existence of a sequence that converges to a value outside of our set. Then every subsequence of that convergent sequence has to go to that same location. So even though we can find convergent subsequences, they're not going to go to a value that stays in the set. So the key to coming up with a counterexample in this case for the set B is to identify that B is not closed and use that to show why we're not compact. So we are not compact, and in order to do this, we have to come up with an example of a sequence in B that doesn't have a convergent subsequence with a limit in B. So I'm going to let xn, we want to think about, well, why is this set not closed? And use that as an example. So to show that this set is not closed, I would say let xn be the sequence 1 over n plus 1. Now, I chose 1 over n plus 1 instead of 1 over n because notice that one of the claims I need to be able to make is that my sequence is comprised entirely of values in the set B. If I used 1 over n and n was 1, then I would get the number 1, and that's not an element of B, so I just need to shift the denominator to make up for that. So then we can say that xn has to converge to 0, and by theorem, every xnk converges to 0 also, since when you have a convergent sequence, all of its subsequences have to go to the same spot. Since 0 is not an element of B, B is not compact, because we have found a sequence that will not have a subsequence that converges to a limit that stays in our set. So the key here is that B is not closed. Any sequence that proves B is not closed will also prove that B is not compact. So now let's take a look at C. So C, remember the properties we have here. This is closed, so we do know that when you have convergent sequences, their limits are going to have to stay inside their set. But it's unbounded. And so the key here is going to be to use this fact number one, that when you have a sequence that diverges monotonically, then every subsequence is also going to have to diverge. And that's how we're going to sort of exploit the fact that our set is unbounded, to show that C is not a compact set. So let's go down here. So C is not compact. So we're going to need to come up with a monotonically increasing sequence, because it's unbounded above, that diverges to infinity. If we do that, all of its subsequences will diverge to infinity as well, meaning we won't even have a convergent subsequence. So here we're not worried about whether or not limits stay inside the set. We're worried about whether or not we even have convergence. So looking at this, a classic example of an increasing sequence would be N. Note here that this choice of Xn is actually a subset of C. And then we have Xn diverges to infinity and is increasing. Thus, every Xnk is also increasing and diverges to infinity. Therefore, C is not compact. So in summary, again, the key here is that C is not bounded. So give an example of a monotonic sequence that diverges. All Xnk will also diverge.